Welcome to lecture number 2 of thermal physics. And today's lecture is all about calorimetry. And you're watching the Nurture series on Enthuse channel. Enthuse is a dedicated English medium channel for all the JEE aspirants. So nice to see you all here. And let me tell you what we are going to do in today's session exactly. We are going to talk about phase changes, but in detail with calculations. Also, we're going to define specific heat capacity, difference with heat capacity, and what is latent heat, mechanical equivalent of heat, water equivalent, so many equivalents out there, principle of calorimetry, mixing liquids, mixing solids with liquids, all of that with questions with me, Shreyas, your physics master teacher at Vedantu, and I'm going live from Pune. And yes, welcome all the young and new warriors and wish you all a very happy Makar Sankranti. Good evening, my warriors. Nice to see all of you wishing each other hello, happy Pongal. And I hope you had a great day at home. I hope you had some nice sweets. I hope you had some nice preparations. And I hope you had some quality time spent at home. And now it's time for some fun with studies. Welcome aboard. Yep, I have recorded very fast, and I think I have taken a vow that probably till I test properly negative, I'm not going to shave my beard. So the moment you see me without the beard, then that's when you know I'm negative. Isn't that a cool way of letting you guys know I'm negative officially? Yep. Yep, Ramya, I'm going to talk about it tomorrow as well. Yep. Thank you for all the love, Gauri. Thank you so much. And thank you for also smashing the like button down there because it means a lot when you hit the subscribe button and also shower your love and also your comments. Thank you so much. And if you have not yet subscribed, please subscribe because when you subscribe only that's when you get regular updates, regular sessions, or else you are going to miss some of the sessions. Also, when you like, it also motivates me, it motivates Vedantu, it also make sure that YouTube algorithm will show you our videos on your homepage, else there is a chance you might miss out on our videos. So let's get started with our session. I hope you guys are all ready. Dil Gul Gya, Good Bola, Happy Pongal, hello Aisha, hello Jermia, hello Ankit. Gulab Jamun, Ankit trying to distract all of us like usual, but it's okay, Ankit. Yes. Um, Aisha, not yet, not yet. Yep. So everybody at my house, at my home, were positive. So all of us have to test negative together. There's no point if one of us is positive, another one is negative. Then also it creates a lot of issues. But only when all of us are negative, that's when I'm safe to travel around and move around. So we have given our results, samples, and hopefully the sample result should arrive by tonight, maximum tomorrow morning, and I'll definitely let you guys know. Okay. Now, um, since you all are aware, in this COVID season, you might have seen the steamer, and most of you at your home, for protecting yourself from cold and cough and all the other throat infections, you might have used the steamer. You heat the water, and the water gets evaporated into the gaseous state that is called as steam. And if you have steam which is accumulated in a vessel and you leave it for cooling for some time, it condenses back into liquid, right? Yes, the steamer. Hi Lakshana, welcome aboard. Hello Belwa, welcome. Similarly, if you have ice and you provide it some warmth, it melts, and when you basically freeze, that means suck away the heat from liquid, it solidifies. These are the three phases, and each process has its own name. Solid to liquid is liquefaction or melting. Liquid to gas is vaporization. Gas to liquid is called condensation, and liquid to ice or basically solid is called as solidification. And in between these three phases, the particular phase or state of matter can have many temperatures. Like water can exist from 0 to 100 degrees Celsius at normal pressures. Steam will only exist above 100 degrees Celsius at standard pressures. ice will only exist till 0 degrees Celsius at standard pressures, not beyond that. And that's how it works. Each material, each compound, each element will have its own melting and freezing points. Yes, it's different. The boiling points, the melting points, they are all different for each of the different compounds and elements. Yep. Now, what is this latent heat? Yes, Sachimama, I'm going to talk about it. Now, oh yes, Suchimama has used it. Even I used it for the first time. I never used to use sanitizers. And oh, by the way, what is that process of converting a solid into gas called? Yes, have you seen those naphthalene balls? What is that process called? You can put it up in the comment section or in the chats. A quiz, a riddle for all of you. I'm pretty sure all of you know it, and if you know it, then just put it up in the comment section. Very good. You guys are very smart. Very good. Very good. Very good. Very good. Okay. Now let's talk about specific heat. What is this specific heat all about? We're going to talk about it. Excellent. Now, see, whenever you change the temperature of a body, it will basically be absorbing some heat or releasing some heat. For the same change in temperature, let's say you want to heat water, let's say you want to heat aluminum, let's say you want to heat a stone, let's say you want to heat marble, let's say you want to heat wood, or let's say you want to cool something. For every degree of change in temperature, the amount of heat that is absorbed or released will be different depending on the material. And it will also depend on how much mass you are heating. More the mass, more the amount of heat you require. Right? So here is how I define it. Observe this carefully. See, the amount of heat Q. So this is basically your heat is directly proportional to the mass, which is basically M. It's also directly proportional to the change in temperature. So to the change in the temperature, and I'm going to call it delta T. So that constant of proportionality Q is equal to M into delta T. That constant of proportionality is called as specific heat capacity. This is called a specific heat capacity, and it completely depends on the material. It completely depends on the material. To give you an example, the specific heat capacity for water is 1 calorie, that's the unit of heat, 1 calorie per gram per degree change in temperature. That's how it works, specific heat capacity. Some books use the symbol small c, that is also fine. Some books use the symbol small s, which is also fine. So symbols don't matter too much over here. You should just know the concept. Okay, you should definitely know the specific heat capacity of water. Okay, I have put some specific heat capacities out here just for your reference. You do not have to remember it, all of them. Only water is very important. So you can see ice and steam roughly close to 0.5 calories per gram degree Celsius. Okay, that's what you need to know. Now, if something has more specific heat capacity, what does it tell you? Okay, if something has more specific heat capacity, put it up in the comment section, my warriors. If something has more specific heat capacity, what does it tell you about that substance? It tells you that you need more heat or less heat. Think about it. For the same change in temperature, if it has more specific heat capacity, it means it needs heat, more heat for the same change in temperature, for the same change in temperature. Very important. It's difficult to change the temperature. You need to provide it more heat for that same change in temperature. Correct. Very good. Now, what is heat capacity? See, we have talked about specific heat capacity. What is heat capacity? Let's talk about that as well. You might have got confused between these two terms. Specific is basically in detail per unit mass. When I talk about a substance per unit mass, it is specific. It's more in detail. That's specific heat capacity. Heat capacity is not per unit mass. It's just per unit change in temperature. Basically, this is how it works. Q is basically M S delta T, right? Now I'm just going to combine the two terms. Which are the two terms that I'm going to combine? I'll just put it in the bracket, M and S. If I combine both of them, all right, and here is what I'm going to write. That I'll put it as C and into delta T. Now this C is just called as heat capacity. This is just called as heat capacity because if you see the units also, you will understand it is calories per degree centigrade. There is no per gram. So C is M into S, mass times specific heat capacity, because specific heat capacity was per gram or per unit mass times the mass will just give you heat capacity. So yes. So okay, here is a simple riddle for you. Okay, here is a simple riddle for you. There is iron, and let's say there is something else. I don't know, maybe water. Okay, there is iron and water. This S is specific heat capacity, and this C is heat capacity. Which one do you think can be same for iron and water? Okay, just put it up. Thank you, MD Ryan. Welcome, and I'm so glad you're following me. And I can assure you, guaranteed success in the next 2 years by the time you crack JEE 2023. Okay, which one do you think will have? Which one will be same? Is specific heat capacity same, or do you think heat capacity can be same? Think about it. C can be same, but S will definitely not be equal. Specific heat capacity will not be equal. Correct. Vijay, you're a little bit late, but you can use your mouse, go back, even in a live class, rewind, come back to the place where we are at 2x speed. That's how you can catch up. That's the advantage of YouTube learning, online learning. Imagine how it used to be in your regular classes. You come late, you missed, and you are not able to understand anything. And you're like, okay, what is happening? I'm blinking stars, right? But now with online learning, okay, you arrive late, okay, cool, no problem. I just go back, I just take the cursor behind, and that's it. I catch up at 2x speed. Crazy, right? I wish I had YouTube when I was studying. Okay, okay, great, very good, user. Yo, now what is molar specific heat capacity? Oh my god, so many terms, and you'll be like, sir, how many capacities are there? This is beyond my capacity now. Oh my god. So, guys, don't get scared. See, generally, when we heat and we talk about heat capacities and specific heat capacities, we are talking about solids and liquids. But gases, do you measure gas in mass usually? Do you generally measure gases in masses, or do you measure it in moles? Think about it. Yes, Suji, you got it right. When will I start fluid mechanics? Kalyani, I finished fluid mechanics. I guess my playlist is not seen. I'll make it available, but I've finished complete fluid mechanics right from statics to dynamics to viscosity to surface tension. Moles, correct. So when we talk it instead of per kg, instead I replace it with moles, it is called molar specific heat capacity. That's as simple as that. So if I write Q is equal to number of moles into okay, S sorry, not S, I just generally use the symbol C then. Okay, so wait a minute, out here, yeah, N C delta T. So this is basically your molar specific heat capacity. This N is your number of moles. This is your number of moles that you have, and the the unit of C will be, calorie per mole per Kelvin per degree centigrade, whatever you want to write it as. That's how it works. As simple as that. Okay, now we will talk about the different molar heat capacities in a separate chapter called as KTG and thermodynamics. Do you know that there are two or even more kinds of molar specific heat capacities? Look at these two processes. The one on the left side on your top is isochoric. That means the volume is constant. The piston is fixed. Can you see that? And the second one, the piston is free to move. That's isobaric process. So the C for different process is different. This is CV, this is CP. I'm just going to make myself a little bit smaller. Yep, you have CV and CP both. You have two different kinds of molar specific heat capacity depending on what process it is. That then, should raise a question. Sir, if gases have CV and CP, why don't solids and liquids have CV and CP? Then some brilliant student, some Pandu will come and say, Sir, what are you saying? Gases can expand and contract, solids and liquids don't contract, and that's the reason why they don't have CV and CP. Really? Do you really think that only gases can expand and contract, solids and liquids don't contract and expand? Think about it. Last chapter, thermal physics, we have dealt only with thermal expansion, right? So even just like gases, solids and liquids also can expand and contract. So there can be different processes. Then somebody will be like, sir, in solids and liquids, you don't measure it in moles. That's why you don't have CV and CP. No, it's not got nothing to do with moles, but it's got to do with the process. So why is it that you have CVCP for gases, but you don't talk about CVCP for solids? This is very interesting question. Yep. So I'll tell you. Yep. Isobaric process is concerned with isobars. Siva, I'll definitely respond to you. Hello, Varun. Welcome. So, why are they named so? I'm going to talk about it in KTG chapter and thermodynamics. We are going to explain it in detail. The CV and CP for solids and liquids. Okay. So, you have to stay tuned till thermodynamics to get to know about it. All right. So, anyways, so what is molar specific heat capacity? Molar specific heat capacity is when to talk about heat capacities per mole per degree centigrade or per unit Kelvin. Okay, so having said this, let's start with some questions. But before that, one last conversion, and that is the conversion from calories to joules. Now, many people don't really understand this mechanical equivalent of heat, they just by heart it. Okay, look at the diagram on the top right of you. It's over my head. Yes, can you see that? Okay. Do you see that there is a pulley? Do you see that there is a mass? Do you see that the mass falls down by distance z? Can you see it falls down by distance z? Okay, it falls down like this. So when it falls, tell me, my warriors, what is lost? When the mass falls, what is lost? Yep, think about it. Okay, think about it. Think. Yes, that is Mayer's relationship, Ramya. Very true. But why Mayer's relationship is only applicable for gases? Why is it not applicable for solids and liquids? And if there is a Mayer's relationship for solids and liquids, what would it be? So it will lose potential energy. And when it loses potential energy, yes, that will get converted. Do you see the thread is connected to that turbine, that paddle? Yes, that paddle will start rotating. So if potential energy is lost, rotational kinetic energy is gained in the turbine, that paddle, it will start rotating. It will agitate the liquid. If the liquid starts rotating, it starts moving, it will gain kinetic energy. If the liquid molecules gain kinetic energy, what do you think will happen? What do you think? Yes, potential energy is lost because it comes down. The mass comes down, it loses potential energy. That potential energy gets converted into rotational kinetic energy. The rotational kinetic energy goes into the water molecules, and if the water molecules get kinetic energy, what will happen? What will happen? Yes, correct. Temperature will increase. Do you see the thermometer out here? The temperature is going to increase. So as the mass falls, you will see the thermal energy, the temperature will increase. So do you see work can be converted into heat to raise the temperature? That's mechanical equivalent. Earlier, people used to think heat is different, work is different. But then later on it was found that wait a minute, actually heat can be converted into work, work can be converted into heat. This example, the work done by gravitational potential energy has been converted into heat of that liquid whose temperature has raised. So the reverse is also possible. So that's basically mechanical equivalent. The conversion factor, because work is measured in joules. and heat is measured usually in calories. That's why you need a conversion factor, work and heat. And remember that 1 calorie is nothing but 4.2 joules. So you should know this. So we, Anishwaran, these are more like one shots, okay? But these are very systematically thought one shots in a way that you will not feel overburdened, or nor will you feel that, oh, there is too less in this. So last lecture, thermal expansion and temperature. This lecture, calorimeter. Next lecture, kinetic theory of gases. After that, we'll divide thermodynamics into 2 to 3 classes. Okay, so that's how we are going to complete. And then heat transfer will have 2 classes. So in the next 1 week or 2 weeks, complete thermo and thermal physics will be done. Okay, including your heat transfer and thermodynamics and KTG and all of that. Very good, getting O. You guys have got it. Excellent. Heat is a form of energy, so it is also a form of capacity of work. Yes, correcto, Suchi Mama. Very good. Oh. Let's go with this question. Oh. Heat energy is gained when 5 kg of water is brought to its boiling point. Specific heat capacity of water is given. How many 1 kg stones you need to lift by a height of 10 meters for the same energy? Okay, let's see how many of you can do this. How many stones? Just think, 5 kg of water, you have it at 20 degrees Celsius. You want to bring it to boiling point. You need some energy, right? So if I now convert it into an equivalent, saying, okay, you take 1 kg stones and you lift it up by 10 meters. So obviously when you lift 1 kg stone by 10 meters, you need to perform some work, you need to give it some energy. So how many such stones you need to lift so that the energy is same as that of heating the water? Let's do this question. So the heat which is supplied, mechanical equivalent, right? Q is same as W. Q is for heating. This work is done for lifting the stones. Interesting question. Heat is mc delta T. Remember, mc delta T or ms delta T, whatever you want to call it, okay, is equal to work done to lift the stone. Remember, the stone's mass is different, so that m and this m won't cancel. Be careful. mgh. Okay, but this is for one stone. Like that, you will have n number of stones, and this is nothing but the number. Okay, this is nothing but number of stones. I hope this makes sense to all of you. Okay, so now let's do this math and see what do we get as the answer. So mass is 5. Specific heat capacity of water is 4.2 kilojoules. So 10 to the power 3 per kg per degree centigrade. Okay, fine. Change in the temperature from 20, you want to get it to 100, which is the boiling point. What is the boiling point? Boiling point is obviously 100 degrees centigrade. So that's basically from 20 to 100, that's 80. Okay, so I'm just going to put 80, that's the change, is equal to mass of the stone is 1, G 10, height 10, number I don't know. Fair enough. So N will be equal to 8 5 is 40. So we have 40 into 4.2 into 10 to the power 3 divided by these two tens from here. So that will be 10 to the power 2. Okay, so that will be 4 into 4.2 into 1 of the 10 and 1 of the 10 here, so 10 to the power 2. So this will be, yes, 4 4s are 16.2, yes, so that will be 16.8 into 10 to the power 2. Yes, so that will be 1680. Just check this out, 1680. Just check this out, my warriors. Are you getting this? Are you getting this? And have you missed any other term? Let's just check. 10 to the power 3. Oh, there was one more zero, is it? Yes, that 80 was also there. Yeah, I'm sorry. Yeah, let's just do one thing. Let's just add that 0 and let's see what do we get. We should get one more 0. So that was one more 0 over here. So into 10. So that will be nothing but 4 into 4.2 into the two tens get cancelled, and you should get this as 10 to the power 3. So this will be 16.8 into 10 to the power 3. So this will be 16800. Yes, it should be option A. Perfect. Perfect. Yes, that's it. Yep. So I hope this is clear. So we need 16,800 stones. That's crazy number. 16,800 stones to be lifted to heat 5 kg of water from 20 degrees Celsius to the boiling point. I hope this is fine. Interesting number, interesting calculations. Hi, Sri Krishna Reddy. Very good. Let's get going. Oh, Ankit, is it? Thank you for letting me know. I'll definitely do the term to sample paper as well with you. And if you guys want it, are you ready for it? I don't know, especially the 12th standard students. If you're ready for it, then please let me know. Then I will do it right away, or else I'll wait for all of you to complete the portion and then probably we can do it. Okay, anyways. Next question coming up on your screen. A solid material is supplied with heat at a constant rate. The temperature of the material is changing with heat input as shown in the diagram. What does the slope of the graph part, which is D, represent? Okay. Yes, Ankit, I know, you are serious. I know you won't kid. Yes, I'll definitely do it. Can I go to thermal physics and thermodynamics without studying mechanical properties? Yes, you can. You can, Salva Kumar. You can. They're slightly, almost like independent. Definitely, you can. Hello, mine actor. So, what is the slope of this graph going to give you? Okay. First of all, what do you think the slope is over here? The representation of the slope. I'll just make myself smaller. See, the slope is the rate of change of y-axis with respect to x-axis. The y-axis is temperature. The x-axis is heat. Correct? Temperature versus heat. Now, what is dq? dq is the heat supplied. Heat is mc delta T. I hope you remember that. Heat is mc delta T. So I can just write it as m. Okay, c or s, whatever you want to write it. ms dt. dt is the small change in temperature. dt will cancel, and you will be just left with ms. Now, what is ms? S is specific heat capacity, m is mass. Specific heat capacity into mass is heat capacity. So basically, what is the slope? The slope is the reciprocal inverse of heat capacity. But which phase is it? Is it liquid or gas or vapor? Think. From here to here, can you see the temperature is increasing? This process is basically the process from A to B. It is basically melting. It is melting. Again, the temperature increases. B to C is liquid. From O to A is basically solid. B to C was liquid. From C to D, it is basically vaporization. And D to E was basically gas or vapor. So it is inverse of the heat capacity of the vapor. Hence option D. I hope this is clear. Very interesting question. Many students get confused whether it is liquid, whether it is gas. So I've explained it to you. I'll repeat. When you start heating, the temperature increases. Then when the melting starts, temperature does not change. Temperature is constant until it completely melts into the liquid phase. And then at point B, think of it like melted ice, which is now converted into water. The water will heat up till boiling point. C is the boiling point. From C to D, it will boil, and then from D to E, it will be in vapor form. That's how it is. I hope this is clear. Very good. That's the answer, my warriors. And moving on to the next question. But before that, in case you still have your doubts which are unanswered and you want to cover the backlogs and you want a revision plan, plus you want to join my batch for 12th standard, plus you want to cover up the 12th standard portions and you want to join the Vedantu Pro subscription and you want to learn in English, then let me tell you that there is a Vedantu course, the 11th standard Pro subscription, which has just started last week. You can take entry into that batch, and that batch will get over in the next few months, and then after that the 12th standard portion will start. So after that you will enter into my 12th standard batch, that too in English. So go ahead, check out that course because you don't have to travel anywhere and you have everything at your fingertips. Going ahead to latent heat. Going ahead to latent heat. Very good, Rafael Sankey. I hope you cracked it, bacha. Your hard work will pay off. Very good. Keep it up. Keep it up. Yes. C to D intermolecular bonds will be broken. Yep. Will you continue the nurture series for 12th standard? Well, Selva Kumar, nurture series, no. It will be called something else. So you'll have a 12th standard course. It will not be called nurture. Nurture is only for 11th standard. Okay, so it will be called by some different name. Okay, so yes, it's not so easy to bring all kinds of languages. Definitely we'll think about it. Yes, but for now you should be happy that we have a dedicated English channel. Just think about it. Anyways, you are going to give the examination most likely in English. Number one. Number two, most of you are in English medium. Number three, eventually when you join jobs or when you go for higher studies, that time you will have to communicate and learn and read, write obviously in English. So it's always better to study, learn, read, write, converse, everything in English. And that's the reason why Vedantu has got English channel for all of you. Okay, so I'm really happy that you have it at least. Okay, chalo, let's get going to latent heat now. Now, what is latent heat? Latent heat means that heat which is required to change the phase per unit mass. I will repeat, latent heat is that heat. So basically, it's the heat required, okay, to change the phase, per unit mass, that's latent heat. So basically the unit of latent heat will be calories per gram. And remember one more thing, phase change is always an isothermal process. Very important. I don't know how many of you realize what this is. It's an isothermal process, meaning until the entire thing changes its phase, you will not see the temperature change. You can try it out. By taking beaker, put some ice and a thermometer, heat it. You will not see the temperature of the thermometer change until all the ice has melted into water. Very important. Yep, it's very important. Keep this in mind. And because latent heat is heat required per unit mass, so the heat required will be the mass into the latent heat. So this completely depends on the material. Very important. Q is equal to M into L. What kinds of L can you have? You can have four different kinds of L, latent heats. Okay, straightforward, you can have four different kinds of latent heats. Example, from solid to liquid and then vapor. So from solid to liquid, you'll have latent heat of melting, correct? From liquid to solid, you will have latent heat of solidification. Don't you see these two things will be equal? Do you guys agree with this? These two things, solid to liquid, how much ever heat you require per unit mass, that's the same heat you require to convert liquid to solid. But yes, solid to liquid, you need to provide heat. It will absorb heat. But liquid to solid, it will release the heat. That's all. Yeah, it is used to break the bonds from solid to liquid. From liquid to solid, the bonds are made. That's why heat is released. Same way, from liquid to vapor, you will need some heat to vaporize it, the exact same amount of heat you need while condensing it. And this will be equal. Yes, it's completely reversible. Correcto. Perfecto. So these two will be the same. So very simple things, from solid to liquid, liquefaction, fusion, liquid to solid, solidification, both are equal. Liquid to vapor, vaporization, or vapor to liquid, condensation, both will be equal. That's it, as simple as that. So latent heat of fusion for ice, fusion means solid to liquid, ice melting into water. You need 80 calories per gram of ice to melt it. For water to convert into steam, you need 540 calories to be given to convert it into vapor. That also means if you have 1 gram of steam and you condense it, you will get out 540 calories. Mean the same. Yep, Suchi. Hi Dinesh, welcome aboard. Very good, my warriors. Excelente. Yeah, so remember these values, 80 calories per gram for ice to water, 540 for water to steam. Let's do the question coming up on your screen right now. The quantity of heat lost in condensing 8 gram of steam at 100 degrees Celsius is how much, my warriors? Oh, no, 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 it is not fission. Be careful. Don't call it fission. Fission is completely different. That is in nuclear physics. Looks like Ramya went to nuclear physics because her favorite topic is modern physics. So be careful. Okay. How much amount of heat is lost in condensing, 8 gram of steam at 100 degrees Celsius? So when you condense, you will definitely need some, sorry, you will definitely get out some heat, which is released, which is lost. So Q will be equal to ml. So start with this. M is 8 grams into L, which is 540, right? That is per gram. Now, whatever answer you get, this will be in calories, but if you look at the options, they are all in joules. How do you convert calories into joules? 1 calorie is 4.2 joules. So this will be 8 into 540 into 4.2. This will be the joules. Is that understood, my warriors? Dinesh, trust me, if I knew Tamil, I would definitely would have taken lectures in the Tamil channel. But since I know Hindi, English, and all of that, so that's the reason why I'll be on this channel. I'll be teaching you physics. I'm not going anywhere. So yes, if you want to learn in English, then this is the channel to be in. We are more than 1 year old now, consistent, providing you free lectures, free content, quality content for mains, advanced, BitSat, KVPY, you name it. Yep. All right. No, no, no. It's not fission. Okay. Yeah. So minus that from 540. No, just do the multiplication and just see how much are you getting, my warriors. Just check this out. 540 into 4.2. If you want, you can just do this. 8 into 54 into 42. Come on, do the math quickly and see if you are getting the answer as 1.81 into 10 to the power 4. Just see if you are getting it as 1.81 into 10 to the power 4. Yes, it is B. Very good, Boxster. Excellent. It seems the calorie is bigger than joule. Yes, it is. Calorie is a bigger unit. So when you burn calories, you should be happy because you're burning a lot of energy. Yes. Let's get going to the next question. The graph shown over here represents how does the temperature change for 5 kg of an substance as it is absorbing heat at constant rate of 42 kilojoules per minute. What do you think is the latent heat of vaporization of that object or that substance? Gram should be converted into kg, not needed. Very good question for the previous one. You don't need it. Reason, this L, which was 540, was 540 calories per gram. So when I multiply it with 8 grams, so that gram will get cancelled and I will only get calories. So that's the reason why I did not convert it. Yes, a lot of people think of converting and then they make a mistake over here. So there is no need in the previous question. Good you asked it, Rafael Sankey. Okay, moving on to the next question. So think about it. There is a graph given and the question is find the latent heat of vaporization. Yes. Now, first of all, understand where is the vaporization happening. Look at the graph. It's not directly mentioned where is the vaporization happening, but you can guess it. See, this part is basically your solid. Okay, because the temperature is changing. This horizontal line is where the solid converts into liquid. So this part is obviously the liquid and this part is obviously the gas part. Now, for vaporization, you need to convert the liquid to gas. So this point to this point, this is the region that I'm talking about. This is where the vaporization is happening. Correct? This is where the vaporization is happening. And see, where did the vaporization start? It started from T is equal to 20 to T is equal to 30. For how long did it go on? Check this out. It went on for 10 minutes. It went on for 10 minutes. Great. And how much energy is it absorbing per minute? 42 kilojoules per minute. So how much heat it absorbed in that time? 42 kilo. Kilo is 10 to the power 3 kilojoules per minute. So into the number of minutes, so into 10. So this many joules it has absorbed, which is 42 into 10 to the power 4. Is that making sense to all of you? Great. Now remember Q is equal to ml. I have given this formula. Q is also equal to, I've told you it is M into L. And what is M? M is 5. So 5 into L is 40, sorry, 1 second. So 42 into 10 to the power 4. That's what it is. So L will be 42 divided by 5 into 10 to the power 4. If you want, you can make that as 0.5. And then if you make it as 0.5, then what do you need to do? You need to multiply it by 10 over here. So that's basically 42 into 2, which is nothing but 84 into 10 to the power 3. That's all I have done. This is joules, but obviously you need to convert joules into kilojoules. So that means the answer should be option C. Correcto. Very good. Very good. Is that clear? Uh, Thank you, Cooper. I will definitely do the CBSE sample paper for all of you as soon as possible. And if you guys want it tomorrow itself, I'll try to do it tomorrow itself. Okay, don't worry. Okay, I'll try and do it tomorrow or maybe on Monday or something like that. Okay, don't worry. Yes, very good. Excellent. Let's get moving to the next question. Very good, my warriors. Now let's talk about water equivalent. Now, as the name suggests, what do you feel? Water equivalent. That means what is the equivalent amount of water needed for something? So I'll give you an example. Say you have some object. It could be, let's say, iron, and let's say you heat it. Let's put some fire on the screen. So this is some heat which you are giving it. So when you heat it by amount Q, so obviously the temperature of the iron is going to rise by, let's say, delta T. The mass of the iron will be M. So I can say Q is equal to MC delta T. Now, if I ask you how much water you need, let's say I take water over here. Okay, this is water. Okay, in a beaker or in a container, and you have to provide exactly the same amount of heat. So the heat that you provide is exactly the same, and if you want to provide exactly the same amount of heat so that the temperature also changes by the same amount, delta T, for water, that amount of water, okay, that mass of water which is there, is called as the water equivalent. As simple as that. This is the mass of the water. The amount of water you need so that the temperature changes exactly by the same amount is called as the water equivalent. It need not dissolve in water, that's it. Just the same quantity of water which when heated by the same amount, the temperature changes same. That quantity of water is called as water equivalent. As simple as that. So simply put, for water you will write Q is equal to mass of water, specific heat capacity of water into delta T. So that's it. Equate these two Q's. From this equation, you will get MW. So can you see MW, CW will be equal to whatever that object is. I don't know. It could be anything. So M into C. So can you see from this equation, MW will be M into C divided by CW. So this is the formula for water equivalent. As simple as that. As simple as that. Okay. Now there is one interesting thing. Usually, specific heat capacity for water in the units that we usually use is 1 calorie per gram per degree centigrade. Usually, so CW is usually 1. CW is usually 1. That means mass equivalent, water equivalent will be M into C most of the times numerically, because the denominator will be in 1 most of the times. Understood? Is class 11th mechanics related with 12th syllabus? Yes, definitely, Laksha. Like only when you are able to do mechanics, you can have that strong visualization, strong analytical skills. And there are a lot of questions which are related to mechanics, even in EMI, electrostatics. You need work per energy in electrostatics and all of that. Definitely you will need it. Okay, let's see if you can solve this question. Come on, my warriors, figure this out. Yep. Now you have, oh, looks complicated, but hold on. It's very interesting. 2 grams of steam at 100 degrees Celsius is passed into a calorimeter containing some liquid. Okay. The temperature of 10 gram of liquid rises from 40 to 60 degrees Celsius as the steam just condenses. What is the water equivalent of the calorimeter and its contents? Let's try to do this question. First of all, you have some steam. Okay, this is our beautiful steam which is entering. This is the steam which is at 100 degrees Celsius. And let's say it enters a calorimeter. Okay, and this is a vague diagram of a calorimeter. Don't take it so literally. Okay, so this is the calorimeter that you have. Excuse me. That was bad. All right. Now you have some liquid in it. I love these colors, isn't it? PowerPoint is so cool. Okay, so we have this liquid, and the liquid which is of 10 grams, the temperature changes from 40 degrees Celsius to 60 degrees Celsius. That is what is given. And when the steam enters inside, what will it have? It will have lot of heat. And then what will happen? Eventually the steam is going to condense. It goes inside and it is going to give that heat, and it just condenses. Okay, it just condenses inside. Now, even the vessel which is there, that vessel will also absorb some heat. Not just the green liquid, but also the vessel. So even that vessel will absorb the heat, and his temperature, the vessel's temperature, is going to change from 40 degrees Celsius to 60 degrees Celsius. The question is, what is the water equivalent of that vessel, that calorimeter? That's the question. Okay, so let's try to do this question. Very, very interesting. First of all, okay, now understand the process where the heat has flown. The heat which was given by steam in condensation process has gone into two things: the heat required for that liquid, the one in green, plus the heat which is absorbed by that calorimeter vessel. Correct? These are the two places where the heat has been absorbed. Makes sense, all my warriors? The steam which was at 100 degrees Celsius, it condenses, it becomes small drops, it loses heat. Where does it give the heat? It gives it to the water and that vessel. That's why the vessel along with the liquid heats up from 40 to 60 degrees Celsius. I hope that makes sense. Now, what you need to do is solve this equation. What is the heat provided by the steam? We have 2 grams of steam, and we know steam gives 540 calories per gram when it condenses. That's the latent heat of vaporization or condensation. So 2 into 540, that's for LHS, is equal to how much heat is absorbed by the liquid? Liquid will absorb, the mass of the liquid is 10 into C. Liquid has a specific heat capacity, that's water, so 1 calorie per gram per degree Celsius. Okay, into delta T. I think there was a mistake over here. This liquid should have been mentioned as water because specific heat capacity of water has been mentioned over here. So that green color liquid is water, guys. So let's assume that, else it will become insufficient information. All right. Anyways, delta T is nothing but 20 plus, remember what is water equivalent? Water equivalent is that amount of water which will absorb the same heat as that of the calorimeter. So think as if instead of calorimeter, you have water inside it. You have water which is absorbing that heat. So that's it. That's all you need to visualize. So think as if it is water. So it was water, how much mass of the water you need? Specific heat capacity 1, change in temperature 20. That's it, as simple as that. Now let's start cancelling the terms and see what do we get. 1 0 1 0 1 0 gone. Acha, one of the two from here and this two also gone. So I'm just left with 54 is equal to 10 plus mw. So mw will be 44 grams. which is option D, guys. On ground, there are a lot of English medium students. That's why I'm teaching in English. And eventually, when you go to a job and when you go for higher studies, you will be studying in English. So that's why we are teaching in English. But yes, you have options, bacha. If you want to study in your local language or you want to study in Hindi or anything else, we have dedicated Vedantu channels for everything. Okay, on ground. Hi Chan, welcome aboard. So that's the answer, guys. Very interesting question. You just have to analyze the situation. If you analyze the situation, you will get it. Else, if you by heart the formulas, you will feel that it is difficult. Number two, how many of you feel that this chapter is very similar to work power energy, where you had to think about which energy got converted into which energy? Do you remember that? Hello, Chan. Happy Makar Sankranti to you too. You had certain forms of energy which got converted into certain forms of energy. Doesn't these equations look exactly like that? Yep, exactly. Yep. So Salva Kumar, there might be some break, obviously. Now let's go to one interesting principle. Won't the temperature of the condensed liquids change? Yep. So Sudarshan, very interesting point that you raised. Here, read the question. The system just condenses. Read this word. Because the word just condenses is used, that means it has now just come to only 100 degrees Celsius. So maybe if you leave it for some more time, that 100 degrees water, which has just condensed, will come down to even lower temperature. So that is beyond this question. So as per the question, we just have to consider only the condensation. We don't have to consider the condensed steam reducing its temperature. I hope this is clear. Very good, Mohammed. Very good, Suti. Very good, Boxer. Excellent. Very good question, Sudarshan. Loving your questions, all my warriors. Many of you have asked very important, crucial, conceptual questions today, which probably has also helped other students. Let's go to the principle of calorimetry. This is very simple. Okay, let's see. Over here, what do we have? We have a hot body. Oh my God, what will a hot body do to a cold body? Okay, and it always happens when you are outside. I think I mentioned about this some days back as well. Uh, Yep, let's say you are sleeping with your friend, cousin, or something, and you are inside a blanket, or let's say you're feeling very cold, and then you just go hug your cousin or somebody because you are feeling cold, you want the heat to be transferred. You want to be in the same room as there are many people in cold weather because you know you will get the heat from others. The room has already been warmed, or that cabin has already been warmed. Exactly. So, the same way, I'm not sure, Rishabh, maybe by mistake. So I would request the moderator to please be careful on whom is being timed out. Yeah, so maybe by mistake. So basically exchange of heat. So when you have a hot body and a cold body together, the hot body becomes cold, the cold body becomes hot, and there is exchange of heat. So the heat lost by the hot body is equal to the heat gained by the cold body. As simple as that, till thermal equilibrium is achieved. This process finally leads to thermal equilibrium. And once thermal equilibrium is achieved, what will happen? There is no further exchange of heat. There is no exchange of heat after this. Keep this in mind. Okay, so only till the process continues, there is heat which flows from hot body to the cold body. Very important. All right, I isolated my cat to gain the heat. Oops. Okay, and what is calorimetry? Okay, no, okay, very interesting question, Suchi Baba. Is it related to disaster management? No. What kind of disaster? No. Calorimeter is basically the study. Calorimetry is basically the study of heat exchanges and how much temperature changes when things are mixed, touched, or in general to heat or cool a body. That's all. Yep. Okay. Thank you, Sarth, so much. And can you do Cengage in the 11th middle? Yes, why not? You can. But I usually don't recommend Cengage for physics. For maths, maybe yes. But for physics, please don't do Cengage. It's not a great book for physics. Trust me on that when I tell you. Okay, if you want to get a good rank, you want to clear JEE Mains plus Advanced, do HC Verma, do Erodo, do Tatva, do Pre-YQ from Aryant. You can also do DC Pandey. Yeah, but yeah, don't do any other book which is not standard. Yes, so yes, Sarth, very good. Very, very true. Sarth is saying, if I get fever and if I'm hot, should I sit next to my brother because he is cold? Yes, you should definitely sit, because then what will happen is, it actually, you will see one very surprising event. It will violate the law of calorimetry. When you sit beside your brother who does not have fever, you will see that instead of you becoming cold and you attaining equilibrium temperature with your brother, in fact he too will get heated up to the same temperature instead of reaching a middle temperature. How is this possible? Very interesting thing, Sarth Matre. Both of you will get heated up, and if both of you go into a crowd full of cold people, then you will see within few days all those people will also get heated up. It will be crazy. You should you should not try this. Yeah. Okay. Okay. Chalo. Let's get going to the question coming up on your screen. Here we go. Two liquids A and B are at 20 degrees Celsius and 15 degrees Celsius, and their masses are also given in the ratio of 2 is to 3 and specific heat ratio in 3 is to 4. The resultant temperature when they are finally mixed is how much? Come on, think about it, my warriors. What do you guys say? Yes, engage. You will not challenge you, bacha. That's the reason, own ground. Okay, let's see how many of you can do this. Okay, Sarth, I'm not sure whether you got my sarcasm, bacha. All right, so there we go. There we go. Let's see how many of you can do this. Think. What would be the equation? Yes, Ramya. I will do it in the modified form, not exactly in its original form, but in its modified form for physics. Okay, because we don't have second law in its basic form, we have it in its modified form. Okay, let's see. A is hot. Do you see this 20 degrees Celsius is hot? B is cold. So obviously they are going to reach a middle temperature. Let's say the equilibrium temperature is T degrees Celsius. So heat lost by A will be heat gained by B. Heat lost by A will be mass of A, specific heat capacity of A into delta T. So T will be below 20 but above 15, correct? So heat lost by A, that means 20 higher minus lower temperature. Be careful about it. Yep. And heat gained by B. Why am I writing 20 minus T? Because I know T will be less than 20, but it will be more than 15. Final temperature will be somewhere in between 15 and 20. So heat gained by B will be mass of B into C of B into delta T. The final temperature is more than 15, so T minus 15. T minus 15 will be a positive number. Both LHS and RHS should be positive. So MA by MB, I'm just showing all the steps, or else I can skip the steps as well, but some of you then might face some difficulty, will be equal to T minus 15. I've just shifted M and C below. The mass ratio is 2 is to 3, heat ratio is 3 is to 4. So 2 by 3, and this is 3 by 4. This is 20 minus T is equal to T minus 15. You can see 3 goes. This will become 2. So 20 minus T is equal to 2T minus 30. So 50 is equal to 3T. So T is equal to 50 divided by 3, which is 16.66. Correct. Degrees Celsius. That's the answer. Just like energy conservation. Correct. It's just like energy conservation. Okay. I hope this is clear. Very good. Interesting. Happy Pongal to you, Thalapati Giri. Thank you so much, and happy Pongal again. Looks like you missed my initial wishes at the start of the class, but that's okay. Here is your next question on your screen now. 500 grams of ice, which is at 0 degrees Celsius, is mixed with 500 grams of 80 degrees Celsius water, which is hot. So hot water mixed with ice. What do you think you will finally get? Will you get warm water? Will you get some other thing? I don't know. You figure it out. Now, these kind of questions are very important because the two substances, okay, the two substances are in different phases. The substances, two substances are in different phases. And these kind of questions have to be dealt very carefully. Why do you have to deal these kind of questions a little bit carefully? Because the reason is you do not know what is the final phase going to be. Think this way. You have ice, you have water. The hot water will melt the ice. But what if the hot water, as it is melting the ice, is not enough to melt the ice completely? Got my point? What if the hot water, as it melts the ice, it will cool down. 80 will become 70, 60, 50, 40. Finally, it will become zero. Once it becomes zero, isn't the ice temperature and the water temperature same? Isn't the ice and water temperature same? That's it, heat exchange will stop. So the hot water can only give heat till a certain amount, and the ice needs certain heat to melt. So we need to see if that heats are sufficient to melt it. If it does not melt, then it's a different story. If it melts, it's a different story. Oh, no, Suchi, it cannot convert into vapor, because if you have 0 degrees and 80 degrees, when they mix, the final temperature will be between 0 and 80. It cannot be beyond 80, it cannot be less than 0. Correct? Yeah. So, yes, sometimes happens. But yes, if instead of water at 80, if you had steam at 100, if you had steam at 100, then you do not know whether that ice will melt, heat, and convert into vapor, or the vapor will condense, cool, and convert into ice, or ice will melt, vapor will condense, and they will come to some intermediate temperature as water. So many things can happen. Do you guys get it? That's the reason why I said the moment you have two substances in different phases, be very careful, alert. You do not know what's going to happen. So calculate how much you have, how much you need. It's just like, a bank, or somebody taking a loan, or somebody borrowing some money. I need something. I need 1 lakh rupees, but my friend only has 20,000 rupees. Then there is no point of me asking my friend, because my friend cannot give me more than 20,000 rupees. But if I have another friend who can give me 1,50,000 rupees, then yes, I can go and ask him, because I need lesser than what he can provide. I hope that makes sense. So that means let's start with the basic calculation. A lot of books confuse students with the way they do these kind of questions, and read and understand and practice my method very carefully. First, see what is there, see what you need. Start with, let's say, for example, for the 500 gram ice which is there at 0 degrees Celsius, if you just melt it, you are just basically melting it and converting it into 500 gram of water, because when you melt it, it will just become water at 0 degrees Celsius. How much heat do you need? Just think about it that way. So it will be M, which is 500, into L, which is 80, which is going to be 5 into 80, sorry, 5, 8 5s are 16. Okay, just 1 second, guys. Sorry. Oh, sorry, 8 5s are 40, my bad. Yeah, 40, 40, and then 1, 2, 3. So this is basically 40 kilocalories. 40 kilocalories. This is the amount of heat which you require to melt the ice. Correct? Great. Now, imagine you want to take this water. If you want to take this water into 80 degrees Celsius, how much more heat you require? Yes, M into L, that's all. You need M C delta T. Delta T is 80. Correct? Delta T is 80. Oh, interesting. I hope this is clear because M is just 500 and C is 1 and the change in temperature happens to be 80. So you need more 40 kilocalories. This is what you need to heat it. Think about the reverse. Think exactly about the reverse now. What is the reverse? You have 500 gram water at 80 degrees Celsius. If you cool it down to 500 gram water at 0 degrees Celsius, how much heat can it give? How much heat can it provide? That's M, which is 500, C, which is 1, into delta T. Delta T is again 80, so that's going to be 40 kilocalories. Interesting. Now think logically. Ice is there. To melt it, how much do you need? To melt it, how much do you need? You need 40. Interesting. And here, that hot water, when it cools to 0, how much heat will it give? 40. Do you see this 40 is exactly equal to this 40? This is what you need. This is what you can give. Isn't the demand meeting the supply? Isn't the demand meeting the supply? Can you see that? This is what you need. So whatever you can give, you're just going to give it. So that means what will happen? The water, hot water will cool down to 0. The ice will just melt. Both the temperatures will become 0. That's it. The process will stop. The process will just stop. And that's it. What will you have? You will just have finally water at 0 degrees Celsius. And how many grams of water? 500 grams plus 500 grams, which is basically 1 kg water. 1 kg water. Hi Darshan. Yes, Ankit, it is indeed amazing. Hi Gitanjali Singh, welcome aboard. Did you understand this question? Did you understand this question? So the final answer is 0 degrees Celsius. Yes, it is 0. It's not 40. That is wrong. No PRDV. So what happened? Ice, when it melts into water, it needed 40. Hot water, when it cools down to 0, it can give 40. Because whatever you need and whatever you give exactly matches. That's it. They will stop the process the moment they reach 0 degrees Celsius. As simple as that. Very interesting question. Beautiful. Let's move on to another question. Beautiful question on calorimetry, and you're going to love this question as well. It can be JEE Mains plus level. Some of these questions can be asked even in JEE Advanced, especially the ones which are asked towards the end of the class. Darshan, I hope you're able to understand because this is 11th standard topic, and I hope you were there from the beginning of the class or you had some background for this lecture. Steam, which is at 100 degrees Celsius, it passes into 1.1 kg of water in a calorimeter whose water equivalent is 0.02 and it is at 15 degrees Celsius. And the temperature rises to 80 degrees Celsius. The mass of the steam which condenses is how much? That's the question. The mass of the steam which condensed is how much? Very interesting question. Do we need to write plus 40 or minus 40 to indicate melting? In which situation? No, you just, it's temperature. Temperature, if it is minus 40, it's in negative temperature. It's in freezing. So you need to put it as 40 or whatever. Yeah. Temperature is in absolute terms. All right. Be careful. Okay. Now let me make you visualize this question first before we go ahead. So here is your calorimeter. Interesting. And again, there is some opening, let's say, and you pass some steam inside of it. You pass some steam. How much steam? Which is at 100 degrees Celsius. 100 degrees Celsius steam is passed into it, and the mass of the steam is unknown, so I'm just going to assume it as m. Fair enough. And the steam will condense, but remember the contents which are there inside of it. So there are some contents inside. I don't know what is there, but something is there. 1.1 kg of water is there, and water equivalent is 0.02. It was initially at 15 degrees Celsius. It heats up because the steam is hot. It heats up to 80 degrees Celsius. So the contents which are there inside, how much contents will you take? Will you take 1.1 kg water only? Think about it. There is also water equivalent of the calorimeter. Water equivalent of the calorimeter should also be considered. Many people ignore it because even the calorimeter is also going to absorb some heat or release some heat. So think of it like water. So apart from that 1.1 kg water, think as if you have 0.02 kg water equivalent. So basically you have 1.12 kg of water. I hope that makes sense. Is that making sense to all of you, my warriors? That 1.1 kg, this is actual water. 0.02 is the equivalent water which will behave like the vessel, that calorimeter vessel. I hope that is clear and that is being visualized by all of you. Yep. Yep. So, Gitanjali, that's what I gave you the summary. The steam entered inside. Steam is very hot. It has a lot of heat. What will it do? It will heat the liquid inside. It will heat the liquid inside. So the liquid, what liquid you have? Water. How much kg? 1.1 kg. So what temperature is it? 15. What will it rise to? 80. So that 1.1 kg water which is there inside, it will definitely get heated up. It will definitely get heated up. Apart from that, the vessel will also get heated up. Think of the vessel like water because the question says water equivalent is 0.02. Whenever water equivalent is given, all you need to do, think as if water only is present instead of that other object. That other object which is absorbing heat is not there, but instead you have water only. Is that now clear, my bachalo? Is that now clear, my warriors? Yep. Oh, I need to make myself small. Oops, I forgot to make myself small. Okay, great. Give me a thumbs up if you got it till here. Now, what happens to that steam which enters inside? The steam which enters inside, it not only will condense, but it will finally, it will condense and it will achieve the same temperature as that of the contents inside. All the contents, the temperature changes to 80 degrees Celsius. So that's the final temperature. It will condense and finally come to 80 degrees Celsius. Clear, my warriors? So steam condensed and went till 80 degrees Celsius. That's what has happened. So once you are able to visualize this much, it's all about now writing the energy equation. How will the energy equation look like? The heat for the steam to basically condense, but there is more. The heat for the steam which was condensed to cool, the condensed steam. This was the condensed steam to cool from 100 to 80. Remember, after it condenses, it goes to 100 degrees Celsius. So from 100 to 80, it has cooled further. So this much amount of heat has gone into heating this water. So this is Q supplied for heating the water. Is that clear, my warriors? Did you understand this equation? So the steam lost some heat. The steam lost the heat in condensing plus cooling in the water form. This much heat, where did it go? To heat the water. Which water? That cold water, 15 degrees Celsius water. Till what temperature? 80 degrees Celsius. I hope this is clear. I hope this is clear. So Q of the condensed steam, that will be M, but that is in grams, I suppose. So into 540. This will make it calories. This will be in calories. Remember, if M is in grams, then to convert calories into joules, because I can see kgs and all of that over here, I multiplied by 4.2 so that finally this becomes into joules. I hope this is clear. Plus, okay, plus the heat which is required to condense it. Okay, what is it? Yes, so Oh, oh, where did it go? Just check this out. Yep, yep. There we go. Yeah. So M into C, which is 1 into delta T. Delta T is nothing but 20. This will be equal to, okay, this will be equal to 1.12 into C, which is 1 into delta T. What is delta T? Delta T is 15 to 80. So 80 minus 15, that's 65. But this is all in calories. So if it is in calories, what will you do? Convert it into joules by multiplying it by 4.2. Also remember this MC delta T over here. This was also in calories. You multiplied by 4.2 so that you convert it into joules. I can see that number 4.2 is there everywhere. I can see that number 4.2 is there everywhere. So what do I do now? I can just cancel that 4.2 from all the sides. I hope you can see that, my warriors. Yep. And just do the math and see what do you get. So you have 540 plus 20, which is nothing but 560 m, okay, is equal to 1.12 into 65. That's what I get over here. So m will be 1.12 into 65 divided by 560. Just do the math and tell me what do you guys get this as. Yep, are you getting option A, 0.13 approximately? 0.13? Yep, 0.13. Yes, that's the answer. That's the answer. Very good, very good. Excellent day. Very good. So that's how you get it. So make sure you solve the homework questions as well. So we have completed calorimeter in today's session. And it was a beautiful session where we have discussed the specific heat concept, phase changes, latent heat, then also water equivalent, and also then we have moved to mechanical equivalent, and then calorimetry, and then phase change related questions. This is your second homework question. Please post it up in the comment section in the after the session is over, and then also do the third homework question for all of you. And yes, if you want to take up the pro subscription of Vedantu, right now there is Pongal offer going on, 50% off. This is a limited period offer. So if you want to take up your pro subscription, Vedantu, you want to attend my classes, my micro courses, and also complete revision test series, also get assignments and the Tattva material, go ahead. Because usually the prices that you see over here are double. So the light price that you see over here is 1500. Right now, you are getting the light at 750. In fact, you are getting the plus, which is having personal mentor and the doubt solving together, apart from the regular features, is at 1500 rupees. So you get 50% off in this Pongal offer. Try it out. You have three versions. Light is everything that you need, like test series, assignments, notes, everything. But if you want the doubt solving to be done, then you need to go to the classic version after the classes. And yes, personal mentorship is available in the plus version. All right, so that's it from my side. Thank you very much. Take care. Have a great time. Thank you for tuning in, and stay blessed, stay safe, and also do the homework and put it up in the comment section as well. Bye bye. Hasta la vista. This was Captain Shreyas signing off.